Jai Hind, welcome to the course Network Analysis and Synthesis, and this lecture is continuation of the last lecture where we discussed the initial conditions and final conditions of a first order and second order circuits. So today we are going to discuss network analysis having initial conditions with using the Laplace transform. So circuit may be RC circuit and RL circuit. So these two circuits, they are the first order systems we can say, and this is the second order system. So today we are going to discuss the circuit analysis RC, RL and RLC having with and without initial conditions using the Laplace transform. So there are two methods or two approaches to carry out the circuit analysis using the Laplace transform. First is to write the equilibrium equations. And then apply Laplace transform. So write the equilibrium equations based upon certain laws, whether we can apply the Kirchhoff's voltage law or Kirchhoff's current law, and then apply the Laplace transform. And second one is convert the circuit in S domain and then write the equilibrium equations. Okay. So there are two methods to carry out the network analysis using Laplace transform. Either we write the equilibrium equations. Here we get integro differential equation. Depending upon the type of circuits. So it is a integral differential equation. So to solve a integral differential equation, what we do? We apply the Laplace transform. So it is here once we convert the circuit in S domain, then here we get the algebraic equations. Once we get the algebraic equations, we can solve the algebraic equations by using the algebraic manipulations, addition, subtraction, division and multiplication. So there are two ways, either we follow this one or we can follow the second one. So in this lecture I am going to follow the second method. First we will convert the circuit in S domain itself and then apply the equilibrium laws to find the equilibrium equations. So if you remember, in the last class we discussed some initial conditions or behavior of the circuit element at t is equal to 0 plus and at t is equal to infinity. If there is resistor, then that t is equal to 0, it is simply a resistor. At t is equal to infinite, it is resistor. But inductor at t is equal to 0 plus, it behaves as a open circuit. We know that the inductor opposes the rate of change of current. So when we switch on the circuit having the inductor opposes the rate of change of current, so it behaves as an open circuit. At t is equal to infinity, inductor behaves as a short circuit. For capacitor at t is equal to 0, it behaves as a short circuit, at t is equal to infinity it behaves as a open circuit. And if these circuit elements, inductor and capacitors, having some initial values, so equivalent at t is equal to 0. So, if a inductor having the current I0, so this is the equivalent circuit at t is equal to 0 plus, and this is the equivalent of the inductor at t is equal to infinity. But similarly, we can have the for the capacitor having the initial charge Q or initial voltage V0. So, at t is equal to 0, its equivalent circuit is like this, and at t is equal to infinity the equivalent circuit is like this. So, this circuit diagram is very useful when we convert the circuit in S domain, or we try to find some initial values in the circuit. So, we draw the behavior of the circuit at t is equal to 0 and then find the initial conditions. So, I will explain this all this with the help of some examples. We also discuss the circuit elements in time domain as well as S domain. Suppose we have a simple resistor. So, in S domain the equivalent will be like this, and this. So, this circuit is, if you apply the Kirchhoff's voltage law, we try to draw the R in this fashion. If you try to apply the Kirchhoff's current law, we try to draw the equivalent R in S domain in this fashion. For inductor, this is the inductor in time domain. So, we can write the simple equations. So, Vt is the voltage across the inductor is L di upon dt. And if you find the current, the expression for the current is It is equal to 1 by L 0 to t b tau d tau, and some initial current through the inductor, that is I0 minus. So, these are the equations, I can say the equilibrium equations in time domain. So, just apply the Laplace transform to this equation, we get this. And once we get this equation, we can write the, or we can draw the equivalent circuit in S domain. So, this is the element in time domain, and this is the equivalent of this element inductor in S domain. So, if just look by looking this one, इसको वो कर देना एडिट, ठीक है ना, ये मेरे को यहाँ दब गया ना, एंड शो कर दिया, ठीक है, इसको हटा देना यहाँ है ना, ओके. So, this is the circuit of inductor in S domain. Similarly, we can have the expression for current in S domain. So, this is the current expression in S domain, and once we have the expression, we can draw the equivalent circuit. So, this is the circuit in S, this is the circuit inductor circuit in S domain. So, here we can see there are two types of circuits of inductor in S domain. So, when the circuit is appropriate to apply the Kirchhoff's voltage law, then we draw this equivalent. Then we draw this equivalent. When the circuit is appropriate to apply the Kirchhoff's current law, then we draw the equivalent of inductor in S domain, this circuit. Now, come to the capacitor. So, this is a capacitor in time domain. So, this is the equations for the current through the capacitor, and this is the voltage across the capacitor, and this V0 is nothing but this is the initial voltage across the capacitor. Once we have written the equations, we can apply the Laplace transform. So, this is the Laplace transform of this equation for the current, and this is the for voltage. So, we can draw the two circuits. So, this is the equivalent of the capacitor in S domain, and this is also equivalent of the capacitor in S domain. So we can get the two different types of circuits in S domain. We use this one when we are going to apply the Kirchhoff's voltage law, and we use this one when we are going to apply the Kirchhoff's current law, right? So these are some basics of the Laplace using Laplace transform to a RL, RC and RLC circuit. Now just do some problems. The first problem is the switch K is thrown from A to B at t is equal to 0. The switch K is at position A for very long time. Current I0 minus flow in the inductor and capacitor is charged to voltage V0 by, and we are required to find the IS. IS means the current in S domain. So this is the given circuit. The switch K is at position A for a very long time. So what you have to do here, in this case the initial conditions are given. Okay. If initial conditions are not given, then what we have to do? We have to draw the equivalent circuit at t is equal to infinity. At t is equal to very long time means time is equal to infinity. So you have to draw the equivalent circuit at t is equal to infinity, find the initial conditions, but in this case the initial conditions are given. So no need to find the I0 and VC0. Okay. The straightway what we do, when the switch is at position B, so the switch is at position B means this is the circuit. So what I have done, I have converted this time domain into the S domain. So Vt, the time, the Laplace transform of Vt is Vs R, and this inductor has initial current I0. So the equivalent of this inductor with initial conditions will be this one. This is the equivalent of inductor in S domain, and this is the equivalent of the capacitor in S domain. Now then we can apply the Kirchhoff's voltage law, because here it is very easy to apply the Kirchhoff's voltage law. That's why I have taken the appropriate circuit diagram in S domain for inductor and capacitor. So once we have converted into S domain, we can write the simple, apply the Kirchhoff's voltage law. So Vs is equal to RIS SLIS minus LI0 1 by SCIS and this. So this is simple algebra, and we can find the IS. So IS is nothing but it is this one. This is the IS. So current in S domain. Suppose find IT. Suppose the question is find IT. So what we'll do? We just we carry out the partial fraction expansion, then the find the number of poles residuals, and then take the inverse Laplace transform. So first carry out the partial fraction expansion, find the poles residuals, and then take the inverse Laplace transform. We can get the solution in the time domain. But in this case, the question is only about the IS. We have to find the value of IS. So simple. Either apply the Kirchhoff's current law, then apply Laplace transform, or convert the circuit in S domain and then apply the Kirchhoff's voltage law. Come to another problem. So the switch is at position A for very long time. So the very long time means t is equal to infinity. Very long time means. Determine the current IT when the switch is at position B. So this is the switch, this is switch, and switch is moved from A to B at t is equal to 0. Okay. So what we'll do? So in this problem initial conditions are not given. So first you have to find the initial conditions. So what we'll do? we draw the circuit at t is equal to infinity, means when the switch is at position A. So, when the switch is at position A for a very long time, so this inductor behaves as a short circuit. So, this is the equivalent, of the circuit when switch is at position A. So, we have this voltage source, then this resistor, and this inductor behaves as a short circuit. Now, we can find the current I0, initial current through the inductor. So, it is very simple, Ohm's law, 10/5, so 2 ampere. So, 2 ampere the current or initial current flowing through the inductor. So, this is the first part of the problem. First, you have to find the initial condition. Now, when the switch is at position B, so when the switch is at position B, draw the equivalent. So, this is the circuit in time domain. When the switch is at this position, so this is the circuit. So, 5 ohm, 5 ohm and 2 Henry. So, here one can write the equilibrium equations applying the Kirchhoff's voltage law, getting the integral differential equation, and then apply the Laplace transform to get the Is, and then invert it to get the It. This is the one way. The second approach is convert this circuit in S domain and then apply the Kirchhoff's voltage law, write the expression for Is, and then take the inverse Laplace transform to get the It. So, I have followed the second approach. So, this is 5 ohm, this is the 5 ohm, and this is the inductor in time domain, and this is inductor in S domain. So, I have drawn this circuit because I am going to apply the Kirchhoff's voltage law. So, I have taken this one. So, this is very simple circuit. So, apply Kirchhoff's voltage law. So, minus 10I, this is the S0, minus SLIS plus LI0 is equal to 0. So, Is is 2 by S plus 5 here. So, Is is 2 by S plus 5. So, it is, if you take the inverse Laplace transform, it will be It is equal to 2 e to the power minus 5t ut for t greater than or equal to 0. So, this is the standard form. If you take the, suppose the suppose Fs is 1 by S plus A. Okay, so Ft is e to the power minus At. Okay, simple. So, here in place of A be 5 and we have the constant. Okay. So, we can take the inverse Laplace transform here because it is in standard form. We can directly write the inverse Laplace transform of this function. So, this is the very simple circuit. Now, come to another one. So, in this circuit, Vt is 5 volt, R is 3 ohm, L is 1 Henry, I0 is given. So, initial conditions in the circuit is given, inductor current and capacitor voltage, these are given. Find the current It when switch is at position B, and switch is at position B. So, what will the current It? So, what we will do, just draw the circuit at when the switch is at position B. So, this is, and convert this circuit in S domain. So, this is the 5 volt DC. So, basically this is like this, it is like this. So, this is 5 ut. We know that for t is greater than equal to 0, ut is 1. Ut is 1. Okay. For t greater than equal. If we take the Laplace transform on this, so we will get the 5 by S. Then resistor, this inductor. So, this inductor we are going to apply the Kirchhoff's voltage law, then we draw this one, SL minus LI0. Similarly, for the capacitor, we can draw the equivalent of the capacitor in S domain and then apply the Kirchhoff's voltage law. So, we can have the 5 Is, 3 Is plus SL Is minus Li 0 plus 1 by Sc. So, simple algebra. Then find the expression for Is. So, this is the expression for Is, 5 Is plus 2 minus 2 by S and this one. So, Is is 2s plus 3 divided by S square plus 3s plus 2. So, what we do? We just S square, this is S square plus 3s plus 2. So, this is the denominator polynomial, ds is equal to, put this is equal to 0, find the roots, we get this one. So, we can take the factor of this one, this. So, we can see that there are two poles at s is equal to minus 1 and s is equal to minus 2. So, the poles at s is equal to minus 1 and s is equal to minus 2. So, there are two poles, so we have to find the two poles residuals. So, similarly we can write this k1 by s plus 1 and k2 by this. So, what is this? This is the partial fraction expansion of this expression 2s plus 3, because we can carry out the partial fraction expansion when the function is rational, and this function is rational because numerator polynomial, degree of the numerator polynomial is lower than the degree of the denominator polynomial. So, we can find the k1 and k2, which is 1 and 1. So, this is for k1, this is k2 and this is 1 by s plus 1 is it was minus t, and for 1 by s plus 2 it was minus 2t ut for t greater than equal to 0. Okay, because ut is defined for t greater than equal to 0, for t less than 0 value of the ut is 0. So, this way we can solve the circuit using the Laplace transform. Now, suppose the circuit dynamics is given, okay, and you are required to find the response of the circuit. Just look at this problem. The system is characterized by differential equation d2yt upon dt square, 5 dyt upon dt square, 6yt ut, and these are the initial conditions of this circuit dynamics, and ut is the unit step. Find the response of the system. So, response of the system means total response. Total response, that is you have to find the yt. We have to find the yt. This problem can be modified. Find the free response, forced response and total response of the circuit. So, how we will do it? So, this is basically a differential equation. So, to solve a differential equation, what we do? We apply the Laplace transform. The simple way, we apply the Laplace transform of the given differential equation. So, for this term we have this is the Laplace transform. For this one we have Laplace transform this expression, and for this we have this one, and ut is the unit step. So, Laplace transform of unit step is 1 by s. Now, separate the term ys and put initial conditions y0 minus is 1 and dy0 upon dt is equal to 2. So, we get this one. So, s square plus 5s plus 6 ys is equal to 1 by s plus 2 plus 5. So, look here, what is this? and what is this? 1 by S is the input, and these are the initial conditions. So what I have done? I have just divided this expression ys in two terms. Expressions involving the input and expression involving the initial conditions. So this is, say this is y1s and this is y2s. If we take the inverse Laplace transform of this yt, of this y1s, we get the y1t, and this y1t is the response due to input. It is known as forced response. If we take the y2s and take Laplace inverse, it will be y2t, and this y2t is nothing but this is response due to initial conditions. So this is known as the free response. So this is the forced response and this is the free response, and both together known as the total response of the circuit. So if the question is find the free, force and total response, so what we have to do? We have to segregate expression involving the input and expression involving the initial conditions. So I have written here. So if we get the response of this one, this term, this will be the forced response, because input is here, and here we have the initial conditions. S plus 7 is nothing but it is coming from the initial conditions. So if we take the response of this y2, it is called free response. So now take the y1s, that is the forced response. So 1 by s plus 2 into s plus 3. Take the partial fraction expansion. So there are 3 poles. So 3 poles residuals k0, k1 and k2. We can find the value of k0, which is coming 1 by s. We can easily get it. K1 is minus half and k2 is 1 by 3. So y1s is 1 by 6s minus 1 by 2s plus 2 plus 1 by 3 s plus 3. So if you take the this is the standard format. This is the standard form. Standard form. So we can write the inverse Laplace transform directly. So the inverse Laplace transform of 1 by s is ut. Similarly, this is also in a standard form. This is also in a standard form. So inverse Laplace transform will be this one. So this is called forced response. Now take y2s. So y2s is s plus 7, s plus 2 and s plus 3. Carry out the partial fraction expansion, find the value of k3 and k4, and we get this k3 is equal to 5, k4 is minus 4. So this is the y2s. Again standard format, we directly write the inverse Laplace transform. So y2t is 5 e to the minus 2t ut minus 4 e to the minus 3t ut for t greater than or equal to 0. So the total response of the system is y1t plus y2t. So you have to find the yt. So just take the summation of y1t and y2t. So this is the total response of the circuit. So what we have done, we have find the force response, then we have find the free response, or we can say the natural response, and then the total response. So in the questions they may ask find the forced response, free response and the total response. Then we have to show the y1t and y2t also. If the question is just for the total response, then we just add on to get the yt. So this is the total response of the circuit. So this is all about your circuit analysis using the Laplace transform. If you combine this lecture and the previous lecture, so we covered the how to get the initial conditions of the circuit and how to find the circuit response using the Laplace transform. So thank you very much. If you have any query, you can write mail to me at rayanil@akgec.ac.in. Thank you very much. Jai Hind.